Welcome to the deep dive. Today, we're really putting on our thinking caps. We're diving deep into the core of statistics and research design, all thanks to the materials you shared with us.
Yeah, some great stuff to dig into.
Our mission really is to pull out the key concepts, give you a clear understanding, but without, making it feel overwhelming.
Think of it as your shortcut, sort of, to grasping these essential principles. They underpin so much of the information we all encounter.
Exactly. And for you, the learner, getting a handle on these fundamentals is just incredibly valuable.
Whether you're navigating research in your own field, maybe getting ready for a test, or even if you're just curious, right? A solid grasp gives you this powerful new lens for looking at information.
We're not aiming to turn you into a stats guru overnight or anything.
No, the focus is on practical understanding, trying to simplify the technical bits, avoid the really complex stuff, unless it's necessary.
Okay, so let's unpack this. Where do we start? Maybe with how we even categorize research. It's not all just numbers.
That's a great place to start. The first big split is qualitative versus quantitative.
Right. Qualitative. That's more about getting a rich, detailed picture, isn't it? Exploring the why and the how.
Exactly. Holistic description, using things like interviews, observations. It's often inductive, building understanding from the data up.
So understanding and interpretation.
And then quantitative is, well, it's about the numbers. Numerical data, empirical methods, things you can observe and measure directly.
Statistical procedures, looking for patterns, predictions.
Yeah, prediction, generalizability, causality. That's often the focus. It tends to be more deductive, starting with a theory or hypothesis and testing it.
And the methods are different too, naturally. Qualitative, you mentioned interviews, observation, also things like ethnographic studies, looking at cultures.
Right. Ethnographic, phenomenological, looking at lived experiences grounded theory, where the theory emerges right from the data. Document analysis fits in there too.
And quantitative, you've got non-experimental stuff.
Like correlational studies, just seeing if things are related, not necessarily cause and effect. Archival research, using existing data, surveys, obviously.
But the materials you sent really emphasized experimental research, didn't they?
They did. That's where we'll spend a fair bit of our time. It's where we really try to pin down cause and effect.
Okay, experimental research. This is where it gets really interesting, I think. Testing ideas about how one thing impacts another.
The effect of an independent variable on a dependent variable.
Yeah.
That's the core.
And there's a process, right? It's not just jumping in.
It's definitely a process. Starts with an idea. That idea becomes a testable hypothesis.
Then you choose your design, how you'll actually structure the study.
Select your sample. Who are you studying? Then you conduct the study, gather the data,
Analyze it.
using statistics usually,
Okay.
and finally, report what you found.
Seems logical enough, but lots of potential pitfalls along the way, I imagine.
Oh, absolutely. Each step needs careful thought. A really key early step is identifying and defining your variables.
Ah, variables. Okay. So, first things first. Variable versus constant.
Simple but crucial. A variable. Well, it varies. It has to exist in at least two different states or levels.
Like gender, if you have both men and women in your study.
Right, but if your study only includes men, then for that study, gender is a constant. It doesn't change.
Makes sense. Now, the big ones.
Hmm.
Independent and dependent variables. IVs and DVs.
Oh, 5e, the independent variable, is the one we think causes a change in the other. It's the treatment or the intervention, often called X.
And in a true experiment, the researcher actually manipulates this, right? They decide the level.
Exactly. They control it. And crucially, an IV has to have at least two levels, maybe a treatment group and a control group, or two different dosages so you have something to compare.
And the dependent variable, the DV or Y, is outcome, the thing we measure to see if it was affected.
Precisely. You don't manipulate the DV, you observe and measure it, often before and after the IV is introduced.
There's a good way to frame the question, isn't there? To figure out which is which.
Yeah, just ask, what is the effect of the independent variable on the definite variable? It usually slots right in.
The studies you shared had some good examples. Study #1, the self-control procedure for kids with ADHD.
Right. So what's the effect of the self-control procedure 4V on academic achievement DV?
Clear. And study #2, the schizophrenia treatment one, that had multiple IVs and DVs.
It did. Two IVs, the type of therapy, and the dose of the phenothiazine drug.
And 2 DVs, scores on the BPRS, that's a symptom scale, and the WAIS-5 intelligence test.
So you're looking at the effects of therapy and drug dose on symptoms and cognitive function. more complex.
Now, study #3, the salesperson one, that was a bit different.
Ah, yes.
Yep.
The organizational psychologist looking at predictors of sales success.
The IVs were product knowledge, attitude, assertiveness. The DV was dollar sales. But the key thing
Was that the psychologist couldn't manipulate those IVs. Product knowledge, attitude, assertiveness, those are characteristics of the salespeople themselves, organismic variables.
So you can see if they're related to sales, but you can't say for sure they cause higher sales based on that study alone.
Exactly. That lack of manipulation, often coupled with no random assignment, limits the causal inference. It highlights why true experiments, where you do manipulate the IV and randomly assign, are powerful for determining cause.
Okay, IVs, DVs. But then there are these other types, mediator and moderator variables. Sounds like things are getting complicated.
They add nuance, definitely. A mediator variable helps explain how or why the IV affects the DV. It's the mechanism in between.
Like go between.
Pretty much. Think back to the ADHD study. Maybe the psychologist believes the self-control procedure works because it increases the kid's self-efficacy, their belief in their own abilities. Mediator. And that increased self-efficacy leads to better academic achievement.
So, okay, 4 affects mediator, mediator affects DV. Like a chain reaction.
Exactly. The wiring in the lamp analogy works well. Switch affects wiring, mediator affects light, DV.
Got it. And a moderator.
A moderator changes the strength or direction of the relationship between the IV and DV. It tells you when or for whom the effect is stronger or weaker.
So in the ADHD example, maybe age?
Could be. If the procedure works better for older kids than younger kids with ADHD, then age is a moderator variable. It changes the strength of the IV's effect.
Like a dimmer switch on the lamp.
That's a great analogy. Moderator is the dimmer. Mediator is the wiring.
Okay, that clarifies things. How, when, for whom adds layers. Now, measuring these variables can't just be vague concepts.
Absolutely not. You need operational definitions, defining exactly how you're going to measure or identify that variable in your study.
Some things are direct, like dollar sales. Easy enough.
Right. Others, like assertiveness or self-efficacy, you might need a specific test, a questionnaire, or maybe systematic observation.
Speaking of observation, the materials went into some detail there. Narrative records, like writing everything down.
Or recording it, yeah, a running commentary. Then you might use content analysis to find themes or patterns in those narratives.
Protocol analysis sounds cool, getting people to think aloud.
Yeah, understanding cognitive processes by analyzing what they say as they solve a problem. Really neat.
Then there were more systematic methods. Interval recording.
Or time sampling. You observe for set periods, divided into intervals, and just note if the behavior happens during each interval. Good for ongoing stuff like on-task behavior.
Versus event sampling.
Where you record every single time the specific behavior occurs. Better for less frequent behaviors or ones with clear beginnings and ends.
Like hitting another child, maybe, or completing an assignment.
Exactly. And you might use situational sampling, observing in different places to see if the behavior generalizes, or sequential analysis to look for patterns in complex interactions.
Like a detective piecing together clues from the behavior.
You got it. Okay, so we've talked about variables and measuring them. Now let's shift to the overall research design, specifically the level of control. This brings up quasi-experimental versus true experimental.
And the big difference boils down to
experimental control, especially random assignment of participants to the different treatment groups.
True experiments have that random assignment.
Yes, that's the gold standard if you want to infer causality. It means, in theory, the groups start out equivalent on all factors, known and unknown, except for the IV you introduce.
So back to study #1. If the psychologists randomly assign kids to get the self-control procedure or not, that's a true experiment.
Correct. Any difference in academic achievement later is much more likely to be due to the procedure itself.
So quasi-experimental, that's when you don't have random assignment.
Right. You often have to use existing groups like classrooms in different schools, or maybe just study a single group over time, before and after an intervention.
So comparing kids in school A treatment to kids in school B control would be quasi.
Yep. Because the kids weren't randomly put into those schools or groups, there could be pre-existing differences between them. Maybe school B has more resources, or the kids come from different socioeconomic backgrounds that could explain any achievement differences, not just the treatment.
Makes it much harder to say the treatment caused the outcome.
Much harder. There are more potential confounding variables, more alternative explanations for the results. Still valuable research, but limitations on causal claims.
Okay. Now, getting the participants in the first place sampling, the goal is a representative sample, right? So findings apply more broadly.
Ideally, yes. You want your sample to reflect the population you're interested in generalizing to.
Mm.
If your ADHD sample in study #1 is very different from the general population of kids with ADHD, your results might not apply to others.
And probability sampling methods help with that.
They do. They ensure every member of the population has a known chance of being selected. Simple random sampling is the baseline everyone has an equal chance. Like drawing names from a hat. Produces bias.
Then stratified random sampling, that's for ensuring subgroups are represented.
Exactly. If things like age or gender are important, you divide the population into those strata groups and then randomly sample from within each stratum. Ensures you get the right proportions.
And cluster sampling.
That's when you sample groups or clusters. First, like randomly selecting 10 hospitals. Then you might study all the patients in those hospitals. Or maybe randomly select patients within those selected hospitals. Useful when a full population list is impractical.
Like the schizophrenia study example sampling inpatient programs first?
Precisely.
Okay, super important distinction time. Random selection versus random assignment. They sound alike, but aren't.
Critical difference. Random selection is how you get your sample from the population. It's about generalizability. Can you apply findings back to the population?
And random assignment
is how you put those selected participants into your different treatment groups, like treatment versus control, within the experiment. That's about internal validity and inferring causality.
Selection for generalizability, assignment for causality. Got it.
You can have one without the other, by the way. You might randomly assign participants you didn't randomly select, for instance.
Okay, now control within the experiment. The goal, the material said, is maximize 5e variance, control extraneous variance, minimize error variance. Sounds like juggling.
It is a bit of a balancing act. Maximize the fourth variance just means make your treatment levels distinct. Make the treatment really different from the no treatment or from another treatment. Make the effect easier to see.
Like strong self-control training versus none at all.
Exactly. Then control extraneous variables. Those pesky confounders. Things that aren't your IV but could also affect your DV.
Like the initial symptom severity in the ADHD kids. If one group starts out much milder, that confounds the results.
Right. So how do we control them? Random assignment is the best overall tool, as it helps balance out known and unknown confounders across groups, theoretically.
But what if you can't randomly assign or want extra control?
Other methods exist. You could hold the variable constant, only include participants with, say, moderate ADHD, but that limits generalizability.
Can't apply it to mild or severe cases then.
Correct. Or you can match participants on the confounder, find pairs of kids with similar severity scores, then randomly assign one from each pair to treatment, the other to control. Good for small samples.
Or blocking. Treat the confounder like another IV.
Yes. You create blocks based on the confounder, mild, moderate, severe, and then randomly assign within each block. This lets you control it and see if it interacts with your main IV. Does the treatment work differently for different severity levels? It essentially treats the confounder as a moderator.
Clever. And finally, statistical control. And in Toliva.
Analysis of covariance. You measure the confounder beforehand, like pretest scores or severity, and then statistically remove its influence on the DV when you analyze the results. Very useful in quasi-experiments.
And the last bit of control, minimizing random error.
That's about reducing the noise, standardizing procedures, making sure measurements are reliable, controlling the environment to reduce distractions or fatigue. Just tighten up the experimental process.
Okay, all this control stuff feeds into validity, right? Internal and external validity.
Big concepts. Internal validity asks, can we confidently say the IV caused the change in the DV in this specific study? It's threatened by poor control over those variables we just discussed.
If internal validity is low, the results are questionable within the study itself.
Pretty much. External validity asks, can we generalize these findings beyond this specific study? To other people, other settings, other times, other ways of measuring things.
Population validity and ecological validity.
Right. And importantly, you can't really have strong external validity if your internal validity is weak. If you don't know if the IV caused the effect in your study, you certainly can't generalize that uncertain effect elsewhere.
But high internal validity doesn't guarantee external validity either.
Correct. There are threats specific to each. For internal validity, we worry about things changing over time within participants, maturation, or external events happening during the study, history.
The act of testing itself, testing effect, changes in measurement, instrumentation, extreme scores moving to the middle, statistical regression.
Groups being different from the start, if not randomly assigned, selection, people dropping out differently from groups, attrition, and interactions between these things.
Phew, lots to watch out for just to be sure about cause-effect within the study.
Indeed. Then for external validity, generalizing outside the study, we worry about the pretests changing how people react to the treatment, interaction of testing and treatment.
So results only apply to pre-tested people.
Potentially.
Yeah.
Or the sample being unique, interaction of selection and treatment. Maybe volunteers react differently than non-volunteers.
Reactivity, people acting differently because they know they're being watched.
Yes, that's a big one. Evaluation apprehension, demand characteristics, figuring out what the study's about and trying to help, or the experimenter unintentionally influencing participants. Experimenter expectancy. Double-blind procedures help there.
And within subjects designs where people get multiple treatments.
Multiple treatment interference or carryover effects. The effect of one treatment might linger and affect responses to the next one. Counterbalancing helps manage that.
Okay, managing all that leads us to specific experimental designs. Group designs versus single subject designs.
Right. Group designs compare groups. Between groups, designs have different people in each condition. Simplest is two groups, treatment versus control.
But they can get more complex, like factorial designs.
Yeah, with two or more IVs. These are great because you can see the main effect of each IV on its own.
And the interaction effect, how the IVs work together, like the ADHD study example where severity, IV1, interacted with the self-control procedure, IV2.
Exactly. The interaction showed the procedure was most effective for mild cases. That nuance is often missed if you only look at main effects. Interactions tell a richer story.
Then within subjects designs or repeated measures, everyone gets all conditions.
Yep. Sequentially, usually, like the single group time series, multiple measures before and after treatment. Good for seeing change, but vulnerable to history effects.
Or giving everyone different drug doses one after another, but then you worry about carryover.
Right, which is where counterbalancing comes in varying the order of conditions. And you have to be mindful of autocorrelation, where scores might be influenced by previous scores from the same person.
And mixed designs just combine these.
Pretty much. At least one between groups IV, example, different therapy types, and at least one within subjects IV, example, measuring outcomes over time. Very common.
Finally, single subject designs. Focus on one or a few individuals.
Yes. The participant acts as their own control. Key features are a baseline phase, A, without treatment, and a treatment phase, B, with repeated measurement of the DV throughout.
The basic AB design. Baseline, then treatment.
Right. Stronger evidence comes from reversal designs like ABA or ABA. You withdraw the treatment back to A to see if the behavior reverts. If it does and improves again when you reintroduce treatment, the second B, that's strong evidence for the treatment's effect.
But not always ethical or practical to withdraw treatment, especially if it works or if the effects are permanent.
True. That's where multiple baseline designs are useful. You apply the treatment sequentially across different behaviors, settings, or subjects.
Like teaching the self-instruction first in a quiet room, then later in the library, then later in the classroom.
Exactly. If the target behavior, like on task, only improves in each setting after the intervention is introduced there, it suggests the intervention is effective and you didn't have to withdraw it. Assumes the baselines are relatively independent, though.
Okay, lots of design options. Now, shifting slightly, scales of measurement. The materials really stress this for choosing stats later.
Absolutely fundamental. Can't pick the right analysis if you don't know your scale. First, continuous versus discrete variables.
Continuous can take any value in a range, discrete only specific values. Dichotomous is just two values.
Right. Then the four scales. Nominal, ordinal, interval, ratio. NOIR is a common acronym.
Nominal, just categories, names, like types of therapy, gender, numbers are just labels.
Math. Basically just counting frequencies.
Ordinal, categories with an order, like rankings, first, second, third, or Likert scales, strongly agree, etc. You know more or less, but not how much more or less.
The intervals between ranks aren't necessarily equal. Math. You can use order statistics, like the median.
Interval, ordered. And the intervals between values are equal, like temperature in Fahrenheit or Celsius or IQ scores.
Now, you can do addition and subtraction meaningfully. Calculate means standard deviations. But the 0 point is arbitrary degrees. 0 degrees C doesn't mean no heat.
Ratio scale, the top level. Ordered equal intervals and a true absolute 0 point, meaning complete absence of the thing.
Like height, weight, reaction time, Kelvin temperature, dollar sales. 0 means 0. Allows all math operations, including multiplication and division. You can say 10 seconds is twice as long as 5 seconds.
And frequency counts, the materials noted, can be nominal, how many people in categories, or ratio, how many times something happened.
Koino, knowing the scale is step 1 for stats.
Which leads us neatly to descriptive statistics, summarizing the data we collected. Frequency polygons were mentioned.
Like line graphs showing score distributions. Shape tells us a lot. Is it normal bell-shaped?
Yeah.
Is it peaked, leptokurtic, or flat, platykurtic? Is it skewed?
Skewness. Tail points to the high scores, positive skew, or low scores, negative skew.
Exactly. Then we summarize with measures of central tendency typical scores. Mode is the most frequent, easy, but unstable.
Median is the middle score when ordered. Good for skewed data or ordinal scales, ignores outliers.
Mean is the arithmetic average. Uses all data, stable foundation for many stats, but pulled by extreme scores. So misleading in skewed distributions.
Choice depends on the scale and the distribution shape, right? Table 2 in the materials summarize that.
Yes, median often for ordinal, mean for interval ratio, unless it's very skewed, then median might be better. In a skewed distribution, the mean gets pulled towards the tail.
Then measures of variability, how spread out is the data. Range is simple, highest minus lowest, but sensitive to just those two extreme scores.
Variance gives a better picture of the average squared difference from the mean. Sum of squares in the numerator.
Usually divide by n1 for sample variance.
Right, for an unbiased estimate of the population variance. Standard deviation is the square root of variance. Back in the original units, easier to interpret. Bigger SD means more spread.
And in a normal distribution, we know those percentages. 68% within 1 SD, 95% within 2 SD, 99.7% within 3 SD.
Very useful benchmark. And finally, how simple math affects these. Subtracting a constant changes the mean-median mode, but not the variance SD. Multiplying, dividing changes both central tendency and variability.
Okay. Wow. That's a pretty comprehensive tour through the fundamentals laid out in these materials.
It is. We've hit types of research, variables, validity, experimental designs, measurement scales, descriptive stats. Quite a journey. The core ideas really revolve around control and experiments, understanding internal versus external validity, and how scales and stats help us make sense as data.
Hopefully for you listening, some aha moments clicked into place. Maybe the difference between mediators and moderators finally makes sense.
Or that crucial distinction between randomly selecting your sample and randomly assigning them to groups.
Or even just thinking about why a skewed distribution might make the median a better summary than the mean sometimes.
Exactly. And maybe a final thought to leave you with. Consider how this understanding empowers you now. When you encounter information, a news report, a claim in your field, even an advertisement maybe.
You can start to ask critical questions based on these principles. What assumptions are being made? Is this correlational or causal? How is this measured? Was there a control group? How were participants selected?
How strong is the evidence, really? This framework isn't just academic. It gives you tools to move beyond just passively receiving information.
To actively analyzing its foundations, questioning, evaluating, making more informed judgments about the world around you.
It's about critical thinking, spurred by understanding the nuts and bolts of research and stats.